Hey all you cool cats and kittens, hope you're doing well. This class is about associative analysis. So associative analysis is the third one that we discuss in Marketing 470. And what I'm going to offer you today is first a little bit more information about what an association between two variables really is. What does it mean when we found an association such as, for example, a correlation between two variables? Then we're going to go over the difference between non-monotonic, monotonic, linear, and curvilinear relationships. This depends on the measurement level of your variable. And then I'm going to teach you two different tests in SPSS. The first one being cross-tabulation and chi-square. These are actually two tests, but they go hand in hand. And then the second test I'm going to teach you is correlation analysis in SPSS. So first thing you need to know is that when you're looking for associations between variables, you could notice based on the analysis you run that two variables are related, but that doesn't mean that these variables are causally related. So it's not because one variable changes at the same time another variable changes that there is necessarily a causal effect from that one variable on that other variable. So correlation does not imply causation. It's not that every correlation you find is indeed a causal effect. If you want more information about this phenomenon, you can look at this video. This does not equal that. This is a very informative video that I'm not going to show in this deck of slides, but you can just watch it as additional information for yourself, which totally explains that idea that correlation is not causation. So why do association tests really matter? So regardless of which field you're in business, you're always going to have to rely on associations between variables, seeing or finding links between concepts in your environment, between variables. For example, if you're working in retail, you may want to know whether the type of product people buy, let's say, for example, if you're working for REI, this very warm subarctic sleeping bag, where are people located? The most likely buyers, where are they located? So you could see if there's a relationship between location of where you live in the United States and likelihood of buying such a sleeping bag, such a really warm sleeping bag. Or is there a correlation or is there a relationship between the credibility of a speaker and appreciation of an audience? For example, in communications, from a communications perspective or an IMC perspective. Or if you're working in the health marketing domain, if you're interested in that for your career, you may want to know if there's a relationship between age and likelihood of vaping or the percentage of youth that actually vapes. Or you could look at the relationship between vaping behaviors and diseases like lung cancer, see if there's a relationship there. Or from a political marketing perspective, you could look at whether there is a relationship between how people vote, so Democratic versus Republican, and basically the color of their skin, whether there is any relationship between ethnicity and voting patterns in the United States. And this map illustrates this really well. This one shows the election results. This was for 2018 midterms, if only non-white people voted. So association tests really look at the relationship between two variables. Now, we either look at the relationship between different levels of that variable or between different labels of those variables. The word labels we use when we refer to nominal or ordinal variables. The word levels we use when we refer to interval or ratio scaled variables. This immediately brings us to the different types of relationships, because these different types of relationships completely depend on the measurement level of the variables in that relationship. So non-monotonic relationships, monotonic relationships, linear and curvilinear relationships. So I'm going to give you a brief explanation of each of them, but what we're going to focus on the most is non-monotonic relationships and linear relationships in this class. Let's start with the non-monotonic relationship. So with a non-monotonic relationship, you basically look at the relation between two labels, between two nominal or sometimes ordinal variables. So this is a very general way of looking at relationships because you don't know the direction of that relationship. All you could say is that in the presence or absence of one variable, there is a presence or absence of another variable. So more than presence versus absence, you can't really say because there's no direction. Because these variables are nominal, there is no direction or no order of magnitude to these variables. Let's explain this by means of an example. So let's say you work in a coffee shop and there's two variables, time of day and type of drink. Time of day is either breakfast, so morning, or lunch, so around noon. The variable type of drink can either be coffee or soft drink. So you have your two variables, one being time of day, breakfast or lunch, second variable being type of drink, coffee versus soft drink. So data could show you, for example, that during breakfast, there's a majority of coffee orders. So you see that 80% of the orders is for coffee and only 20% is for soft drinks. Whereas with lunch, when lunchtime comes around, these proportions flip. So you see that when lunch is present, you see a presence of soft drinks or an overwhelming majority of soft drinks as opposed to coffee orders. These types of relationships can be assessed by means of a crosstab chi-square analysis, which I'll show you in SPSS. Monotonic relationships are different in the sense that they can tell you a little bit more about the direction of the relationship between those two variables. So you could mention that there's either an increasing or a positive relationship or a decreasing or a negative relationship between these two variables. However, you don't have an indication of the exact amount of change. So all you could say is that as one variable increases, another one increases as well, which would be a positive relationship, but you don't know exactly how much each variable increases. So the increments are not necessarily possible to determine. So a good example for this would be the relationship between the stage in a child's development and their amount of control. So basically how much decision power they have in their life. By the way, this here is a picture of me when I was a kid. And what I want to show with this example is that as you grow older, you get more decisional autonomy at every stage of your development. You get more autonomy, for example, in terms of what you decide to wear, what you want to eat, where you go, and so on. So you get more freedom as you grow older, but there's no exact amount of change. You can't say that with every year that you grow older, you get, let's say, 10% more decisional autonomy. It just doesn't work that way because it's not a linear relationship. It's a monotonic relationship. So we can say that there's overall an increasing or a decreasing relationship between these variables, but we can't say the exact amount of change that occurs. Another example would be MTV Cribs. I don't know if you remember that even. That was from my time when I was a teenager. I don't watch TV anymore, but the two variables here would be income and housing size. So you could say on average or overall that as income increases, people's houses tend to increase as well, housing size. So usually higher income means bigger house, but it's not a linear relationship. It's not for every buck you make extra, your house grows 1 square foot. It's not a linear relationship at all. So this is another example of a monotonic relationship. Now here's a linear relationships, which I'm sure you're familiar with from previous classes. This is called a straight line association between two metric variables. So here you have metric variables. So the measurement level must be ratio or interval for these variables to have even a chance of having a linear relationship. So this straight line formula is y equals a plus b times x. Y is the dependent variable that you're trying to estimate or predict. A is your intercept, b is your slope, and then x is the independent variable that you use to predict or explain a dependent variable. Now, this formula is also used for regression analysis, which is the next class, which is a type of predictive analysis. So of course, like I said earlier, correlation does not mean causation. So when we draw conclusions based on correlational data, we can't make any causal conclusions here. So we got to be careful in how we word our conclusions. An example of a linear relationship would be, let's say you work at Chipotle and you want to know the total revenue at the end of the day. And for this example, let's keep it very simple. Let's say 100 customers walk in, so X equals 100 customers, and they each spend $10, exactly $10 per person. So your slope is 10. The intercept in this case is 0. Your outcome variable or your dependent variable is total revenue at the end of the day. So you could say that, okay, if 100 people walk in and they each spend $10, so B equals 10, X equals 100, you have at the end of the day $1,000. So why is the intercept 0 here? Can anyone make any guess on why the intercept is 0? So the intercept is 0 simply because if no customers walk in, no revenue is made at the end of the day. So your intercept is always the value of Y when X is 0. So if X is 0, if no customers walk in, if x here would have been 0, then the slope doesn't even matter, because 0 times whatever is always going to result in 0. If no customers walk in, you'll have no revenue. However, in some cases, especially in the restaurant industry, you could have an intercept that is not 0. Let's say you are a waiter in a restaurant and you are getting paid a base salary, and then on top of that you get paid with tips. Then your base salary that you make regardless of how many people come into the restaurant and how many tips you make, so your base salary will already be set somewhere above 0, and then on top of that you supplement that with tips. So that would be an example of an intercept not being 0. Now, if you have a positive slope, so if your B is positive, let's say every person who comes into Chipotle spends $10, you'll have a line that goes upward. If you have a negative slope, let's say every person who walks into Chipotle takes $10, then yeah, you're gonna have a negative slope for sure, and then this would be a 0 slope. And then lastly, curvilinear relationships are oddly shaped. So they are curved instead of a straight line. So you can have S-shaped curves, J-shaped, U-shaped, and so on. So a common example is the relationship between the amount of anxiety people can experience and their test performance. So usually, you know, it's kind of a cliche, but they say that too low anxiety or too low adrenaline is not going to make you perform really well, but a moderate, like optimal amount of anxiety is great for performance. However, if that anxiety gets too high, if it flips too high to the other side, then of course your performance is going to go down as well. So that would be an example of a inverted U-shape relationship, so a curvilinear relationship. We're not going to test these in Marketing 470, we're only sticking to the linear relationships here. Another example of a curvilinear relationship here is this graph, which is pretty interesting. This is a chart showing the gun deaths in Florida, the number of murders committed using firearms over the years. And you can see that at a certain point here in 2005, Florida enacted its Stand Your Ground law, which is a law that is more lenient towards the use of firearms. And you can see that after the Florida enacted that law, Stand Your Ground, the amount of murders suddenly went down, or seemingly went down. It crashed. So that makes it seem like that law is really good because it lowered the amount of murders using firearms. But however, if you look at this graph more closely, you will notice that the axis here, the y-axis, is inverted. So instead of, after this law was put in place, murders going down, they actually went steeply up in the years after that. So this is incredibly misleading. I want to show this graph to you because I want to make sure that you understand that the way you make a graph has huge implications for the interpretation of your results. Now, if an audience is not looking carefully, is not closely paying attention, they could totally misinterpret this data and think that the Stand Your Ground law has actually improved in the sense of lowered the amount of murders using firearms, whereas in reality the opposite is true. So the source of this graph is Florida Department of Law Enforcement. Not trying to bash them here, but from a research perspective, their graph creation is pretty awful. So keep in mind that when you create graphs, you want a very accurate and truthful, non-misleading representation of your data. Now, how do you assess relationships? So the first thing you want to look at when looking at relationships is whether there even is a relationship present. So first you look at presence. Second, you look at direction. Is this relationship positive or negative? So is it an increasing or a decreasing relationship? And then lastly, you look at the strength of the relationship. How strong is that relationship? Is it strong, moderate, or weak? So you always want to assess relationships in this order: presence, direction, and then the strength of that relationship. So we will revisit these 3 steps of assessing relationships when we look at the results in SPSS. This is a more detailed step-by-step procedure for analyzing relationships. I'm not going to go over that in this online class. You can just read it yourself. This is pretty straightforward and basically builds on what I just said on the previous slide, those 3 steps. Now, what is really crucial here is that you have to look at the scaling assumption, so the measurement level of your variables, before determining the right analysis to do. So, for example, either you work with interval or ratio scaled variables or nominal, sometimes ordinal variables, and this is going to influence what type of test you do. For 2 nominal variables, you want to use cross-tabulation chi-square. For 2 scaled variables, so metric scaled ones such as interval or ratio, you want to use correlation. So this is incredibly important not to mix those up. Here's an overview of the tests that we're going to cover in Marketing 470 when it comes to associative analysis. First one is between 2 nominal or ordinal variables. These are non-monotonic associations. And the test we're going to do is cross-tabulation chi-square. Secondly, after that, we're going to look at 2 metric variables, which means a linear relationship, and we're going to do correlation analysis. So let's start with the first one, crosstab chi-square. So like I said before, with crosstab chi-square analyses, you need 2 nominal or ordinal variables. So this test is actually 2 tests that go hand in hand. You have a chi-square test, which tells you something about the presence of a relationship. Is there a statistically significant relationship? And then the crosstab part of the test examines the relationship patterns. So what does the relationship look like? What's the direction, what's the strength, and so on. So that's why we use both these tests in conjunction with one another. So a crosstab basically displays the non-monotonic relationship between 2 nominal or ordinal variables, and it does so by creating a crosstabulation table. And a crosstabulation table consists of rows and columns. So let me show you a couple examples of crosstab tables. You can basically show the raw frequencies, you can show the raw percentages, you can show the column percentages, or you can show the row percentages based on the same data. So there's different ways of looking at crosstab tables. Let me give you examples. So what you have right here is 2 variables here at the bottom. So there's 2 types of people, buyers versus non-buyers of craft beer, and then 2 types of occupations, professional workers and manual workers, so white collar and blue collar workers. So the 2 variables are 1, type of person, 2, variable 2 is type of occupation, type of profession. So if you look at a frequencies table with data in it, a very simple crosstab table, you could see the actual raw frequencies here. You see there's 152 people who are buyers of craft beer and also white collar workers. 8 people are non-buyers of craft beer and are white collar workers. 14 people are buyers of craft beer and blue collar workers, and 26 people are non-buyers of craft beer and blue collar workers. This makes for a total sample of 200 people. So these 200 people, you can look at these raw frequencies in a crosstab table, and you can also tell that if I were to ask you how many white collar workers do we have in our sample in total, like how many total white collar workers, well, that is 152 plus 8, so 160 white collar workers and only 40 blue collar workers. And we have 166 buyers of craft beer, out of which 152 happen to be white collar and 14 happen to be blue collar. And we have 34 non-buyers of craft beer, 8 of them being white collar workers and 26 of them being blue collar workers. So this is a way to dissect the data in just simple raw frequencies. So let me show you what a raw percentages table would look like. Here's a raw percentages table based on that same data. So again, we have that 152, 8, 14, 26. We have a total sample size of 200. So the actual raw data doesn't change. So what you do show here is the actual raw frequency divided by the grand total of 200. So each of these cell frequencies, 152, 8, 14, and 26, gets divided by its grand total right here, the total sample size. And this is how you get these percentages right here. So you see how much percent of your sample is a buyer of craft beer and white collar worker, how much percent of your sample is a non-buyer of craft beer and a white collar worker, and so on. Now, another way to look at the data is by means of a column percentages table. And here, instead of dividing these raw frequencies, 152, 8, 14, and 26, by their grand total, you now divide them by their column total. So total of the column, which in this case is 166 right here and 34 right here. So 152 out of 166 is 92% of buyers of craft beer are white collar workers. Now 8% of all your craft beer buyers is blue collar worker. Keep in mind, we can't talk about the grand total anymore because now we're doing column percentages. So in this case, we divide by the column total. Non-buyers of craft beer, if we look at those, we see that 24% of them are white collar workers and 76% of them are blue collar workers. So if you inspect this data for a little second longer, you will start detecting patterns. So you will start to be able to see that there is indeed a relationship between buying or non-buying craft beer and whether you are a blue or a white collar worker. So what do you notice here? Again, feel free to pause the video and study the graph for yourself a minute. I'm going to give the answer right now. So you notice that the majority of buyers of craft beer are white collar workers, and you see that the majority of non-buyers of craft beer are blue collar workers. So if you're working for a craft brewery, you're going to find most of your customers in the white collar professional group rather than in the blue collar group. Now, a fourth way of looking at this data is by row percentages. So with row percentages, you again have your cell frequencies, 152, 8, 14, and 26, and you divide them by your row total, 160 in this case, and here 40. So you work with the same data, but you have different percentages. So here you read the table horizontally because you work with the row percentages. You can say that of the 100% white collar workers, so of all the white collar workers, 95% of them buy craft beer, 5% of them claim they don't buy craft beer. And of the 100%, or the total amount of blue collar workers in this sample, 65% of them says they don't buy craft beer, and 35% of them says they buy craft beer. So this is just a very different way of looking at the same data. So I hope with these examples you get some idea of what a cross-tabulation table looks like and how you can look at it. So the most meaningful ways to look at it is by means of the column percentages or the row percentages, because they give you insight in these patterns of relationships between the two variables that you're studying. Now, okay, cool. We can look at these patterns all day long, but how do you even know if a non-monotonic relationship is significant to begin with? To determine this, you need to look at your chi-square value. And your chi-square value, so that's the other component of this analysis, it comes with a p-value. And if it is lower than 0.05, that means you have too little support for H null. So probably you could say that there is most likely a significant association or a systematic relationship between your two variables. And in that case, you can start looking for that pattern that we discussed. So again, that p-value is going to be the determining factor to find whether your relationship, your non-monotonic relationship, is significant or not. So let's do this in SPSS. I have a separate video, as always, for each of these analyses, but I'm going to show you with screenshots in this online class as well. Analyze, descriptive statistics, crosstabs, and then within the crosstabs dialog box, you click statistics, and under statistics, you select the box of chi-square. If you check that box, it'll produce a chi-square output with that p-value. So let's say we want to look at whether there is a relationship between gender and the type of Instagram accounts they follow. So we have gender split in male, female, and other, so the coding being 0, 1, 2. You know from previous classes about coding that you could also do 1, 2, 3. That doesn't, really affect your data. But here the coding is 0, 1, 2. And then different Instagram accounts ranging from 1 to 8. People could check which Instagram account they actually follow the most. So this is what you do in SPSS. You click Analyze, Descriptive Statistics, and then Crosstabs. And under Crosstabs, this window will open up. And as always, on the left side, you can select the variables you want to assess. So you click in Favorite Instagram Accounts and you click Gender. So one of them you click in row and one of them you click into columns. It doesn't matter which one goes where. Honestly, you could have put gender right here and you could have put favorite Instagram accounts right here. You could have flipped them, it's totally fine. The only thing that's going to change is the way your table looks, because if you have a lot of rows, it's going to be a very long table. If you have a lot of columns, you're going to have a very wide table. So it really changes the way your table will look, but it won't affect your data. Now, next thing is you click statistics and you check this box chi-square. If you forget to check this, you will only get half of your output, so you will not be able to make any interpretation about the significance. So whether the relationship is significant. So because the chi-square value is what comes with your p value. Next, you click cells, and under cells, this is already checked by default. You can keep that on. You want to check either row percentages or column percentages. You could do both, but then your table is going to get a little bit bulky. It's going to be too much. So just click one of them. I would recommend in this case row percentages. And then you hit OK. And this is the output you get. So the first thing you see is here overall you have your sample size, 1,000 people. And here you have your Pearson chi-square p-value. Asymptotic significance two-sided. So here's your p-value, 0.020. So what you see here is that the p-value is smaller than 0.05, which means we do find a significant relationship between these two variables. So let's take a look at what that relationship looks like. So let's take a look at our crosstab table. And this is what it looks like. This is the next part in your output. You see male and female. Apparently other does not have a column. That's because no one checked other in this survey. So we only have males and females. Favorite Instagram account: fashion, beauty, lifestyle, brands, sports, celebrities, memes, cartoons, outdoors, and so on. You can start looking at these percentages because we clicked the row percentages, so you see that they add up in rows. So this 100% gets split over 52.7 and 47.3, so you read horizontally. So what do you notice in terms of the gender split or the gender divide for each of these Instagram accounts? So you see that of all people following fashion and lifestyle, you see that the majority is male. Interesting. Anyway, of all people following brands, you see that, or preferring brands, most are male. Another interesting results to cherry pick right here is that there's an equal 50-50 split when it comes to following sports and celebrity accounts. Interesting. 50-50 split right here. Where do we see the biggest differences? Okay, here, food. Oh, interestingly, so 70% of people who picked food as their favorite Instagram accounts are male, not female. Pretty interesting as well. So anyway, this table really shows you what those differences are. And as you can tell, based on my interpretation of this table, it's a little more subjective. I wouldn't say subjective, but it's a little more cumbersome to analyze a table like this because there's no clear-cut answer. You're going to be looking at the percentages of males and females in this case, and favorite Instagram accounts to determine what the relationship looks like, and you're going to report that verbally. So this is a slide that sums up how to interpret the results. First, you want to look at the presence of the relationship. So we found that there is a significant non-monotonic association between gender and Instagram accounts, and we report that p-value, which was smaller than 0.05. So yes, we did find a significant relationship. Next step, remember, step 1, step 2, step 3 to assess relationships, we look at the direction. However, with non-monotonic relationships, we can't really look at a direction because they are nominal variables. So you can't really say anything about a direction, right? So the best thing you can do is detect some sort of pattern. So looking at that crosstab table, you can report verbally in a more subjective way based, again, not really subjective because you have those percentages to back up any claims you make. But looking at those percentages gives you some idea of the relative strength and direction or pattern of those relationships you found. Now, the second test we learn or we cover in Marketing 470 is correlation analysis. So this is a way to assess linear associations between two metric scaled variables. So this is very clear cut. So with a correlation analysis, your output produces a correlation coefficient, non-capitalized r, so lowercase r, which is an index number between -1 and +1. So it always ranges between -1 and +1. And this number, this tiny number, communicates the strength and the direction of your linear relationship between your two metric variables. So there's a lot of information just in this little number that is being given. So it's awesome because just looking at this number, you get information on both the strength and the direction of your relationship. The direction is determined based on the sign. You can have a negative relationship or a positive relationship. So a decreasing or an increasing relationship. The strength of the relationship depends on the absolute size of the number. The closer it is to 0, the weaker your relationship will be. But the closer it is to either extreme, so either -1 or +1, the stronger your relationship between those two variables is. So a correlation coefficient, in essence, really indicates the degree of covariation between two variables. Now, what is covariation really? Covariation means that the amount of change you find in one variable and that is systematically associated with change in another variable. So if one variable changes and along with it another one changes as well, that means really covariation. To what extent do they move together? Now, of course, the greater the absolute size of your correlation coefficient, the stronger that covariation between your two variables will be. Now, when we talk about the strength of a correlation, there's a couple rules of thumbs that help you determine what is a strong versus a moderate or weak relationship. So I'm not going to ask you to memorize these. These are just indications of what we consider a weak versus a strong relationship. Usually when your correlation coefficient is somewhere fluctuating around 0, so anywhere between positive 0.2 and negative 0.2, you're going to have a very weak or non-existent relationship. And of course, as soon as you go over 0.8 in absolute value, so that could be positive 0.8 or negative 0.8, you'll be dealing with a very strong relationship. And these are pretty hard to find. Usually they're fluctuating somewhere more in the middle with moderate and weak relationships. The sign of the relationship determines the direction or shows you the direction. An example of a positive relationship would be the relationship between how much alcohol you drank and your likelihood of falling off of a table dancing. And another positive relationship is, so the more you drink, the more likely you are to throw up the next day or same night. And then an example of a negative relationship is the more alcohol you drink, probably the less happy you feel the next day when your hangover kicks in. So this is an example of a negative relationship. Now, correlation analyses can be explained or can be visualized in a scatter diagram or scatter plot. So in this case, we have a relationship between number of salespeople, so how many salespeople are on a team, and then territory sales, so absolute sales. So what you have here is a scatter plot showing with all sorts of different dots. All of these dots right here are true data points. When these data points form an ellipse, so when they are close to one another and forming an upward ellipse, you actually have a positive relationship. So what we do in correlation analysis is really assess the scatter diagram, scatter plot, to get an indication of our correlation analysis. So if you have a scatter plot with data points scattered all over, and it's not really possible to draw a straight line through all those data points, you have a correlation coefficient that is going to be close to 0. Now, in this case, when you have a correlation coefficient closer to 1, your ellipse is going to look downward, so all your data points will be scattered along a line, more or less along a downward pointing line. And then a correlation coefficient that is positive 1 would be data points forming an ellipse that points upward. Now, of course, a correlation coefficient that would be exactly +1 would mean that the data points need to be exactly on that line. So there's no residuals, no vertical distances between each data point and the line. So we will cover this more in detail in the next class about regression analysis, but for now it's really good to know that covariation can really be shown or displayed using a scatter diagram, and that the direction and the dispersion of your data points is an indication of your strength of your correlation. So how we do this in SPSS is we click Analyze, Correlate, Bivariate, and then you click in those variables you want to analyze, but of course keep in mind you can only click in ratio or interval scaled data. That's because we're doing correlation analysis only on metric scaled data. So let's say we want to know if there's a relationship between different lifestyle profiles and the desirability of a standard size gasoline car, so just a basic car. So lifestyle profiles are assessed by means of 4 profiles, each measured on a scale from 1 to 7. Does not describe me at all versus describes me perfectly. So this is a metric scaled variable. And then desirability for a standard size gasoline car is also measured by means of an interval scaled variable ranging from 1 to 7, 1 being very low desirability versus 7 being very high desirability. So these two variables meet the requirements, namely being metric scaled, to use a correlation analysis. So in SPSS, we click Analyze, Correlate, and then Bivariate. And when you click Bivariate, this window opens up. On the left side, you find your variables you want to analyze, and you would click in desirability for a standard size gasoline car. And then we click in those 4 lifestyle profiles: innovator, trendsetter, mainstreamer, and classic. So it's totally fine to click in all 4 of them at the same time. If you want, you could do only 2 at a time. Either way, since we are doing bivariate correlations, the computer program is only going to analyze 2 at a time. So it's going to create pairs and look at the correlation between 2 at a time. So it doesn't harm by inserting more variables at the same time. You're just going to have a bigger table that could be a little clunky or a little bigger to interpret. Next thing, you want to make sure that Pearson correlation coefficient box is checked, because otherwise you don't get your Pearson correlation coefficient. And then all the rest is checked by default, so that is good. You want to click OK, and then here is your output. So this is your output table, and it really shows you a lot of things at once. What you have right here is different columns with each of the variables, and then here you have different rows with each of the variables again. So you could almost really draw an imaginary line diagonally through your table, through your output table, and that would really be a mirror on the left side, lower side versus upper side, because you see that there's a cross point between each of these variables. So for example, lifestyle trendsetter, cross point with trendsetter right here. This one meets itself right here. This one meets itself right here. So you have this redundancy in a way, because you have a mirroring effect. You have everything twice. So we can actually just look at one of these columns and look at how each of these 4 lifestyles correlate with the desirability of a standard size gasoline car. So let's look at the first one. For each cell, and I know it's not very well marked off, so it's kind of hard to see, but what I'm going over right now is one clump of data you want to analyze. So the relationship between being an innovator or considering yourself an innovator and desirability for a standard size gasoline car, is it significant? Well, that will depend on your p-value here, 0.000. It's smaller than 0.05, so yes, we have a significant relationship between this variable and this variable. Now, if we want to look what that relationship actually looks like in terms of direction and strength, we look at the Pearson correlation coefficient. It is negative, and it is fairly weak. Is it close to 0? So we have a weak negative relationship. What that means in human language is that the more people consider themselves innovators, the less interested they are in a standard size gasoline car. So the less desirability they have for a standard size gasoline car, because this relationship is negative. Let's look at the next one. Is there a relationship between considering yourself a trendsetter and desirability for a standard size gasoline car? The p-value tells us there's none. So the p-value here, 0.491, is larger than 0.05, so there is no significant relationship between these two variables. Let's move on to the next. Is there a relationship between considering yourself a mainstreamer and standard size gasoline car desirability? P-value is again larger than 0.05, so there is no significant relationship here. And then finally, considering yourself classic and desirability for a standard size gasoline car. Here we see that the significance value, or the p-value, is significant. So it's smaller than 0.05, so we did find a significant relationship between these two variables. And if we look at the Pearson correlation coefficient, we notice that it is positive because there's no minus sign in front of it. So we have a positive relationship, and it is moderate, I would say, or almost fairly strong. So a correlation coefficient of 0.634 positive means that the more people consider themselves classic, the more they are interested, or the more they desire a standard size gasoline car, which makes total sense because it's a pretty basic classic car. So people who consider themselves classic are more likely to want that car than, let's say, people who are considering themselves innovators. Innovators might want to go for an electric car instead, let's say, or an electric bicycle. Something like that. So this is really what a correlation coefficient table can tell you. You could, of course, also look at the overlap between all of these other different fields. So you could look at whether there is a correlation, for example, between being a trendsetter right here and being an innovator, and you see that there is 0.000, so there is a significant relationship between these two, but it's a weak and negative one. Either way, it's not very meaningful, because what we are interested in this analysis is the relationship between each of these 4 lifestyles and the desirability for a standard size gasoline car, not with these other lifestyles, but anyway, you get that in your table as well. Now, how do you interpret the results? First, again, you look at presence. So is there a significant association? Check your p-value. So if it's smaller than 0.05, you did find a significant correlation. If it's larger than 0.05, you have no significant correlation. Next, you look at the direction and the strength. The direction can be told based on the sign of your Pearson correlation coefficient. If it's positive, you have a positive direction. If it's negative, you have a negative direction. You could also look at the scatter plot. Strength is also determined by your correlation coefficient, so it ranges between -1 and +1. The closer to 1, either in positive or in negative sense, so the closer to either of those two extremes, the stronger your relationship will be. If it's closer to 0, you'll have a weak or no correlation. So the main takeaways from this class really is that, first of all, you need to use the correct test based on the measurement level of your data. So if you want to look at a relationship between two variables, first determine the measurement level. If these variables are nominal, you want to do a crosstab chi-square. If these are interval or ratio, you want to use correlation analysis. And then also keep in mind that correlation never demonstrates cause-effect. So you cannot make any causal conclusions based on correlational analysis. So for causal conclusions, you need a regression analysis.